Hello, hello. We're back. Back to this. So. Yes. Last time we left off with kind of like an issue with the closures. That is a kind of, I guess, limitation on our pointers, or yeah, instructions like the locations. So basically it's kind of like we have a pointer that needs to be double dereferenced, and we don't really have a way to do that right now. I guess maybe we can have a number. How many dereferences we're gonna do, I don't know. Hello Polaris, welcome back. And Samath, welcome back as well. Yes, it's nighttime. Yeah, for me it's 8:30 in the evening. A little bit of an evening stream for me. Hello, hello. So yeah, so that is what we're trying to figure out here. It's nighttime. For you. What time is it for you? Let's see. Spacing studies of 100%. Yeah, that's fine. You should focus on that first and foremost. 12 instead of watching me. 12:55. Okay. So like wait, 12:55. That's like 4.5 hours. I didn't know there were like half-hour time zones. The more you know. Yeah, I feel like I need to get some more bird's eye perspective on this issue here. So we can look at the blueprint here for creating a closure. So this is basically creating a closure. I'm just going to also double check that this is now how we currently do it. So yeah, we have the saved R closure save R. I'm just gonna name this the same. So that is created first. The closure is created here, and then that is returned. And then we have like the fork. However, then we insert a bunch of instructions here as well. So then we have to look at closure, this one. So pre-instructions. So we set that to R. We allocate to set closure to R. And then we set the closure content. Euro time. Yeah, Sweden. Yeah, exactly. So it's like a evening, late evening, I guess, stream here. Probably not gonna go for very long. I just wanted to, because there was not much left on this particular task, so I just wanted to kind of finish this up here. Yeah, that's the closures, and then we have the fork. However, before we do that, we actually do this now. So we set that there to restore before we fork, and then comes the fork. And then we also set this back to R, and we pop twice. So now basically R is equal to the fork thread handle. Because we're setting that here, and then we get that over here. Yeah. Hello, Penguin. Yeah. I was busy today, but I had a little bit of time now. I just wanted to finish up this last small thing here before. So. Why are you writing comments in the codes? Sometimes that's a good. It's a good thing. Most of the time I actually don't write comments, to be honest. But sometimes I actually do write comments, but not very often. But this part is because it's basically because this is my new language, and I'm trying to figure out what this code that I'm writing here in Runic will become in the IR language. So basically it's because I have two, I'm kind of creating two languages at the same time. No, it's for me. It's so that I can understand what algorithm I want to have when we are in this scenario here, so that I can properly create that later. Because it's easier to write it like this. This is kind of like pseudocode over here. I'm writing pseudocode, and then then I've also implemented it in the actual like compiler over here. I just wanted to kind of double check so that we now have the first, because the way that I did it first is like, first I had the blueprint pseudocoded here, then I did the real thing, but then I had to make some adjustments to make sure that it actually works, and now I'm adjusting the blueprint back to what we actually have in the compiler. Yes, the language on the right here is Zig. Yeah, I just like to be over explanatory because I don't know what you know and so on. I always do that when I explain stuff because it's like, it's better to go from the beginning like be extra detailed, because you might misunderstand something, or the person that I'm speaking to, not just you know, might like miss something and then have a false assumption that will lead to a major misunderstandings later. which have happened like a lot of times. So that's why I've learned from that, and I'm always like explaining very, or well, to a certain extent, detailed. You're studying flowcharts and pseudocode really of zig-like. Yeah, okay, flowcharts. You mean like, yeah, those like UML diagrams, or? We also studied those back in the day when I went to school. I would say like the flowcharts are probably the things. Well, we studied a bunch of other stuff as well, like for UML, but flowcharts is basically the best thing that came out of that. But usually, like UML is like not really used that much, or at least in my experience. Like you're not writing specification, like you're not writing a bunch of class diagrams or specifications like that normally for everything. It's like very, very seldom that happens. It does happen though sometimes, but then it's like, okay, but then it's like it's pretty simple. It's pretty easy to understand what you're looking at. But yeah, I mean, the thing is like, even if someone goes to you and say, like the thing about writing comments or not writing comments, the thing is like, even if someone goes to you and say, hey, never do this or never do that, it's like there might be some situation where where whatever that person is saying could actually be applicable. It's like, why limit yourself? Like I always think of each situation. I try to find new ways of doing things all the time. But I guess, yeah, it's I don't know if it's different when you're learning from scratch. It could be different though, but I just think that you shouldn't limit yourself, basically. That's what I'm trying to say. Like there's always a good tool for everything. Probably. Isn't it crazy? Yo Blue, welcome back. Isn't it crazy that the inventor of ice cream didn't get Nobel Prize? What? Who invented ice cream? That feels like a super old thing. Or are you talking about more recent things? Vanilla ice cream. Logical order sequence with different symbols and shapes. Yeah, the flowchart thing. Yeah, I know about flowchart. As I said, we learned that in school. Like, but there's like it goes under a larger umbrella, which is like UML. There could be other umbrellas as well, but that was like a standard thing. And you learned a bunch of different like diagram types and stuff, but it wasn't really used that much. Next plan is to learn Python after C. Interesting. Is that because like is that how they do it in your school, or is it your personal thing? Everyone should ditch Python and start writing Julia. Okay, I've never looked at Julia. I heard good things about it, but I think I like glanced at it at one point, but I don't know. I didn't get like any special impression from it. Let's see. Okay. Also, in my language, when we say a J, we pronounce it like Julia, not Julia. So that's why I say it like that. But it's probably more proper to say Julia, because that's like an English. But we also have the name in Swedish. But then we don't say Julia, we say Julia. 4 jobs interviews and make my progress. Okay, nice. Yeah, just keep on that. That's a very good that you do that. Yeah, there's like a couple of languages that does like say J like that. And I think there might be, there was something with adopting like the Latin letter or something, I don't know. Swedish. Have you written any Julia, Blue? What kind of language is it? Like, do you know it? Alright, so we have this closure here. This is creating a closure. So really, the problem is when we're referring to the closure. Like, here is like we're declaring, like creating the closure, I don't think is the issue. The issue is when we kind of try to refer to things in the closure. Like, what pointer are we gonna use? Because it's gonna be like a sort of a double dereference thing. Because this goes to the address stored in S3. So actually, this is kind of like this is not really what we want. Basically, what we want is, I mean, kind of like this, like double dereference. Like first, we dereference to get like, or in like more common syntax, I guess, something like this. So we dereference this, because this is just a pointer to the stack, right? This is a pointer to the stack, and we dereference that. That means that whatever is stored in the stack at this point, which is the heap allocated closure, we go to that location, and then we get the first element of that area, which is the same allocation over here. So X there, and then the same thing here. So really what we want to have is like a double dereference. Or wait, actually, yeah, because we want to then dereference, because yeah, X, I mean, yeah, it does point to the closure, first element of the point of the closure, but then that thing in itself is also could be is what we want. So it's kind of like, This, yeah, this would be the thing, but we don't really have a way to do this. That's the thing. Now to say hey in Swedish. Very good. Yes. Hey Monica. How did you know about that? Lingonberry jam. Yeah. Lingonberry jam. Have you tried that? Do you have lingonberry? I know that lingonberry. I mean, it's not like the only place where lingonberry exists, but I don't know where it grows. Like in the world. But it's pretty common up here. It's like a sour, sweet berry. It's very nice for like we usually have lingonberry jam or not really jam, but lingonberry. I don't really know what they've done to it. It's basically raw lingonberry, but they've done something to it. I don't really know. But then it's good for like, you know, meatballs with mashed potatoes and gravy sauce. Are you still working on thread stack management? Kinda. Well, I kind of moved away from the thread stack thing because I realized that was not the issue. And even if we had implemented stack, the thing with the thread stack implementation that I was thinking of, it was gonna lead to like other problems like life cycle issues, where, you know, if the thread that you're referring to has ended, then that stack is basically invalidated. So it's better to store it on like a so what I did was I store a closure on the heap, and I populate that with whatever variables we need to have, and that is implemented now. However, there's one small detail left where the variables that are pointing to the closure needs to kind of be double dereferenced, and we don't really have a mechanism for that right now. So I'm trying to figure out if that is what we need and what we can do to make that happen. But I think that is kind of the last puzzle that we need to solve, the last piece in this puzzle that we need to solve. And when that is solved, we can refer to variables like this from outside scopes and outside threads by creating these closures. However, there's also one small quirk as well where mutability is an issue. I mean, for constants, everything is fine, but for mutability, let's say you want to have a variable out here that is mutable, and then you want to like modify it over here, and that doesn't really work with this approach, because this is like copied into a closure, and then that copy is then modified. So it's kind of like we have to keep it's kind of like we have to kind of keep track. I mean, I guess mutable variables are probably gonna be stored on the heap always then, maybe, I don't know, because if they are, then it's actually mutable, then we can mutate it, I guess. But yeah, that's also like a little quirk there that we need to solve. Food, different species you can come to India, best different dishes, really. Yeah, we have a, I mean, I'm not sure if it's like authentic, but basically some of the best restaurants we've had around here locally have been like Indian restaurants. Although I'm not sure if it's like, you know, super authentic, but we have one right now that is really nice. But expensive, but it's worth it sometimes. But then I also usually just order the same thing every time. Is echo same as printf? It displays output in the screen. Yes, with like. Okay, so echo is okay. Let me show you here. So okay, let's make a new. So I'm not sure if you're familiar with Bash, because that's what we're trying to do. Like this is kind of like a Bash script. So, but I'll just show you in Runic. So echo, hello. Okay, this will just print hello world, right? And then there's also printf. But the thing is, like, these are executables. So you're calling an executable. So these are like Linux executables right now. And it's just calling this executable with this argument. And the same for printf. If you were writing like a bash script, it probably has some built-in plugin that is running some echo, so it's not exactly the same, but it basically is. So, but if I run printf here, I get an error because I don't know why I got an error there. Probably something due to the refactoring going on here, or the implementation that we're doing here. But basically here you can see that this is only one line now. So the difference is that echo will always add a new line to the end, whereas printf will not. There are other differences as well, but now they should be the same. So now we have, well, okay, this doesn't actually, I have to kind of do this. See, we get one thing, echo, remove that, we get the same thing. Printf, we remove it, we don't get a new line at the end. However, let's say you want to say echo and then add another new line here. Now this doesn't actually work. You get this here. But what you can do is you can add the E flag and then you get a double new line. Yeah, it doesn't do formatting. Yeah, so good timing there. It doesn't actually, echo doesn't do formatting automatically. You have to add the E flag. I'm learning this in my college, university, sometimes being with Linux commands. All right, cool. Yeah, and you know, those kinds of things are something that, sure, you're gonna learn a bunch of stuff, like, but the thing that you will remember later is things you will use, like things you will repeat, and you're gonna learn new things all the time. Because even the liksom, oh sorry, that was a Swedish thing. Even the commands that you learn, I mean, they have a bunch of flags. Like all the Linux, like those basic, like they have like a ton of different flags and stuff. And also like the bash scripts, like it goes super deep what you can do. So so yeah, let's see if we can figure this out. The thing is, maybe because we know that we have the thing on the in the closure. Maybe we can actually push it on the stack. No, that doesn't work. Bash Rico POSIX can do so many things. Guys running entire 3D renders. Yeah. You could do a lot of things. But I would say the 3D renders are probably I mean, if you're going for something like that is probably more like a, you know, a kind of fun project to do, and not really for commercial use. Because it's like Bash is like it's the same principle that I have with Rundeck. Like Bash is not for writing any kind of program. Well, you can write sort of any program, but if you want to write something that is like optimized and stuff, you would use like a quote unquote real programming language that would actually compile to something. But it is very good for like quick and dirty scripts to help you with some kind of workflow or something. Bash is also great because it's huge one-liner hacks. Yeah, it could be really like if you learn, you know, if you go a little bit deeper, you can do a lot of things just on the in the terminal, just doing you know, those things. You just want to solve some like a specific problem at the moment, and you just write some bash in the terminal directly. What's about C language? I mean, C is still used a lot, but it's, I would say it's like a very specific areas. It's like used a lot in like embedded programming, I believe. I'm not an expert in that, but I mean, I know, at least I know it used to be. You can probably use like other languages as well, but for when you have like limited resources and you really need to have an optimized system. I mean, Zig could replace C though. All right, godnatt. Man. Yeah. All right. I'll see if I pop in tomorrow. We'll see. It depends, because we kind of have a lot going on in my day job right now, so I'm not sure how much time I have over for this. But yeah, C is good for beginner Although, I mean, I would say like if you want to focus on like core programming principles, I would say like Python is also very good because it's kind of like a newbie starter language that doesn't enforce a bunch of rules that you could learn maybe later. I mean, it does create kind of like a barrier. Like if you're coming from Python and you want to learn C, that is like a pretty difficult step, I would say, compared to the other way around. But like you will still learn, you know, the basic programming concepts more easily, I would say, in Python, because you don't have to deal with the static types, you don't have to deal with pointers and memory allocation, you know. And you can start writing, like you don't even have to begin with functions, you can just write code directly. With Zig or Rust or CPP, you have no idea why the abstraction exists, so it feels arbitrary. I don't know, I feel like Zig and C is pretty close. Like Zig, I feel like Zig and C are pretty much on the same level. Especially like because you can go in and see everything that is going on, basically. You can go into the standard library if you want to see what everything that's going on, which is really nice. All right, see us here. I'm Swedish. Moz, welcome. All right, good luck. I don't know, maybe that's just me. I don't know, what kind of abstractions are you thinking about that's like, that sets C apart from, or that sets Zig apart from C? Yes, I was talking to the person who asked if I was Norwegian. Ever been to Visby? No. Or, I mean, yes. I was there. They have like a Medeltidsveckan. It's like I think every summer they have, I think it's every summer anyway, they have like a kind of like a festival for, I don't know, Medeltid is like Middle Ages or something. But I think it was a long time ago. I just wrote Zig. I don't know, I thought it was high level. No, it's pretty much the same as C. I mean, it has... I don't see too much difference, to be honest. Like in... Like it doesn't. It has manual memory manage. I mean, C++ does that as well, of course, and Rust, I believe, as well. But of course, it's like it depends on what you build in to it. Like you build the abstractions if you want. Like you don't need to. And it just has a different standard library for stuff as well. I mean, I guess C is kind of very close to the operating system, But yeah, so there is, you could say there's like a small amount of abstraction against the operating system in Zig, where you don't work with, like, for example, like you don't work with like the return value of, let's say, because all operating system or in Linux returns like 0 if successful, or I think it's like a negative number if it's like an error. And that is not what's happening in Zig, because that's not how Zig works. It's like Zig have error types, and so it's trying to use that. So there is like a layer of translation going on there. And then of course you have the standard library. But I mean, the thing is, like, everything is visible. Like, you can go in to the standard library and see how those translations work and how they are doing it. And whatever code you're writing is like, okay, well, it's abstracted. That is only against, I would say that's only part of like the standard library. Like, code that you write are basically, I would say, very close to C. What I mean by that is I mean, yeah, the statements that you write, the variables that you declare and all that is very close to C, like how that it works. Is it summer season? You could kind of say it's like, you could kind of say that Zig is, you say you start at C and then you move one step of like, I don't know, 100 towards C++. Maybe that's where it is on the scale or something like that. Is it summer season to yes or no? I mean, it's winter. How many hours of sleep? 7, 8 is good. If you can get it. I mean, I trust science. I'm not a life guru or anything. I can't tell you the secrets to the meaning of life. And you shouldn't trust a random person on the internet for that. But I would say, I think the science tells you 7, 8 hours. Otherwise, you would get like problems later on, like early dementia and stuff like that. Probably. Like, I don't know. But like, if someone comes to me and says like, "Hey, I only need like 3 hours of sleep," I don't really believe that. Like that, I feel like that is. Then you have problems. If you only sleep like 3 hours, you actually need more. It's like we're all human creatures that share kind of, the same biology. It doesn't make sense that. The studies that has been done shows that is how it is. You should try to sleep more if you only sleep 5 hours. But yeah, it is genetic. It does vary from person to person. But I feel like I don't know. You should talk to a doctor or something. you should, you should investigate that, because yeah, it's rare, as they say. But it's like, do you feel tired? And you know, the time for you right now was what? 1 o'clock? So you should be sleeping, right? It feels like you have time to sleep right now. Basically, you should go to sleep. I mean, yeah, I sleep like right now. I sleep because of circumstance. Like, I think I used to sleep like 7-8 hours, but because of circumstances right now, I sleep like 5-6 hours, and that's, I mean, I feel tired all the time. So there is, you know, you can feel difference. Yeah. All right. It's good that you did the work. Yeah, but go to sleep then. Don't talk to me. Go to sleep. Good night. I'll see you later. Alright, I need to figure this out here. Yeah, as I said, the problem is like this part here. Yeah, bye bye. So, yes, hey door. Go to sleep. Do it now. You should avoid screens before bed. Yeah, probably. I have like different periods where it's like, okay, well now it's like, well, the goal is to go to sleep. Sometimes I feel like turning everything off helps, although it's hard. But then also, like, sometimes I put on some speed run or something, because it's kind of like mildly interesting. So I put on a speed run, like a long speed run, and then I just watch, and then I automatically go to sleep after, I don't know, a couple of minutes, 10 minutes, 5 minutes. I don't know what it is, but it usually works. Although the problem is sometimes the brain needs more interesting things. And the brain craves... I don't know. I never got into like doom scrolling, but I kind of feel when it happens. It's kind of the same feeling you get when you play like an idle game, which I've done a fair share of, unfortunately. I am a sucker for idle games. Because it's just a mindless activity. And you get but then you kind of build up a feeling of wasting time. It gets stronger and stronger, and it's also like, well, if you're playing like an idle game that it's not interesting, it just has these very common mechanics, then it's like, okay, well, now I've seen everything that this game has to offer, so now I don't have to like, play until the end. I just delete it. Journey into the cosmos puts me to sleep very quick. Oh. Microcosmos, I guess. It's a misspelled there, but it's the atoms. Or, I guess what's more interesting maybe is like microorganisms, maybe, I don't know. Is it or microcosmos? Is that like atom stuff, or is it everything in between? Like you zoom in, you scale down. But yeah, speedruns for me is like, it's because the way the reason why I go to sleep, I think, is because it's like interesting enough for me to click on it, but then when you actually watch it, it's like you're slowly drifting away and kind of losing interest. Because it's like, I don't know. It's something that is like mildly interesting, I guess. It's just footage of things. Okay, bacteria. Okay, right. Yeah, because it's always like, yeah, that looks cool. That's interesting. You see that the thumbnail, you click on it, and then when you actually get the content, it's like, okay, well, now I kind of understand what this is about, and then you click away, or you go to sleep, or whatever. If we would put this in like notations, like a pseudo program notation here, we would be like, well, it's the stack. This is an address, so we dereference that. Another way to look at it is basically saying heap, the heap pointer, and we dereference that. So now we're in. No, wait. No, that's not right. S3. This is the heap pointer. So we could say that the heap is equal to S3 dereferenced. Because S3 is a pointer to the stack. And then we dereference that to get the value of the stack at that address, which points to the heap. So now X would actually be the first element on the heap. So this is kind of what we want to have. And this is why it's double dereferencing, because here's dereference of S3, and then here's dereference of that. But then we also access element whatever. So if we put this into the usual notation, this would be like this, and then this would be like this. So it's like a double dereference here. It's kind of like I mean, maybe this is the solution. No, well, no, because we don't have a way to kind of do this here. Yeah, we don't have like a recursive location. Alright, see ya. It's connected with sleep because it's like making you sleep when you watch it. Yes, because this part cannot be another location. That's the thing. Maybe we could allow it though. Or we just introduce like double dereference. Okay, let's just solve the issue like that. So this is the thing, like we have mod, which is like, you know, adding or subtracting, modifying the address of where we want to look. And then we have the reference. But maybe we can... Because what we're doing is we're doing this. So first we have the stack and we dereference that. Then we add and dereference again. But I mean, the problem really is this is not a representable thing in the instructions. I mean, it could be a two-parter, like we're doing here. Basically, we're pushing whenever we want to use X, we can push. Or use R or like some kind of generic register, but we push basically, you know, S3 plus 0, so that's the heap pointer. No, we actually have to use a register. We actually have to use R. We set R to that. To the heap pointer, and then we can use this, because then now we can actually use like the normal notation. Like if we do it like this, we don't actually have to we don't actually have to modify the location mechanism if we just add this instruction. But then we need to also store. We also need to save S as well, or I mean the R register. So that's the thing. It's like, yeah, whenever we use X now, if we fetch it from the closure, it's kind of like having multiple instructions returned. Like instead of just returning this location, we actually have like multiple things returned. Yeah, I don't know, man. It's that's gonna be complicated, I think. Maybe. All right, let's just make a special thing for this. Maybe actually, you know what? Maybe we'll actually make a special heap location, or not heap location. What's it called? Not heap, but closure. Actually, we'll make a special closure location. So we could add a new thing here, which would be the closure location, which would be just an index into which closure we're talking about, or not which closure, but which element in the closure. Right. The problem here, though, is that we can't turn it into an address without context. Unless we store the address. Wait. Let's see. I think this is like only used. Here is context though. Oh, where is this? Is used in the evaluator, and here we should know the context here. Although actually, hang on. We could do this. No, not here. This would actually be an error. But then over here we could have closure plus closure address that we can get from here, because that is then very much gettable. Okay, so closure address, which is put there. And I guess this would be like C. closure. All right. Dereferencing. Okay. So then the compiler will say so there's some closure thing going on here, and then closure initialization. So actually, no, it's when we declare the closure value here. So here we do like location dereference. The location is not stack 3 now. The location should be closure index. Actually, let's do it like this. Because we don't really need that to be anything, actually. It's just a closure. It's just C. We don't need a use size because we already have that mechanism for locations in general. So we don't actually need to have like an address stored inside. So let's do that. All right. So you would be closure, and then we add. So actually we just do this, and then we add index to the closure, and then we also dereference. No, we do that later on. Okay. I mean, we could dereference here as well, but yeah. All right. Well, I guess we can keep the to-do until it's fixed. All right, so we have this special type of location called a closure, and we add so that will point to the closure, of course, address, and then we can add to get to the element in the closure, and we dereference that to get to the value of that thing. Okay, so now we have to implement this in places. Dereference value. So for that, I think yeah, I think we'll. Yeah, we can't. This an absolute address cannot be turned into a closure because we don't know if that is what we have. So that should be the same thing there. What is this? Resolve location, right? So now you need two things. You need the stack frame, but then we also need the closure as well. So and the closure address is going to be stack item number 3, which we should always have So it's simply going to be stack 3 and that in turn will always be an address so there we go, because we can look at when we do a fork, we push resolve location closure. That should point. That should be a heap location. And we're turning it into an address here. Yes. Good. So there we go. And here we have, what's this? This is the set instruction, evaluation. And right, so when we set, okay, so now it's like, okay, what if we want to set a thing in the closure? It's probably gonna be like heap. So let's copy that. And this doesn't have anything there. Okay, so we'll get the address. It's gonna be not heap, but it's gonna be thread stack, no, private stack items 3. Very good way of like getting the closure address, by the way. This is not gonna jump. I mean, we could just, to get all the references, we can just do this. So it's fine. But we'll get the address to where we want to be, and that is basically going to be the same thing. Like it is going to be on the heap, and then if we want to dereference, we're going in the thing there. Yeah. That's gonna be the same thing. Okay. Cool. And that's that. Okay. Let's see if that works. No. Unsupported address type. Right, bindings. Okay. Is it from the compiler or where is that? Unsupported address type. Oh, it's over here. To address, right. So where is that called? Here? Probably? Maybe? Or here? The reference location? But since we have the thread, we can do with context here though. We can do 2 adders with context. Okay, index out of bounds. I'm pretty sure every thread should have the stack. Okay. Every thread except the main thread, actually. I just remembered. The main thread actually does not have that, but it should. I'm just gonna add it. Yeah. But it's basically gonna be empty. It's just gonna be to make it work here. Evaluator. Where is that happening? I guess we can just push something. We just push something somewhere. We can also do it in the forward standard IO instruction, because this is where we add this. Yeah. This should really be become the kind of initialize instruction or something. Initialize main thread instruction. And this would be the value is like an address. It doesn't actually matter. Actually this is like it's like a null. No, we don't have that here. Okay. Yeah, it doesn't matter. This is like not used here for compatibility reasons. Okay. Just so that it shares the makeup of every other thread as well. Okay, we still have issues. Access of union field address while thread is active. Thread? What? That is strange. Wait, where is this happening? Dereference location. Streaming. Right. Thread. Why is thread there? Like, I would understand if it wasn't, if it was not existing, but it says that it's thread, so it gets like overwritten by some kind of thread. Okay, well, let's see what's happening. So let's do debug, and I wanna say disable standard IO skip. So here you can see that here's the closure for the main thread. Obviously it doesn't really have a closure. Why does it say thread 1 here? That is not correct. That is very strange. Okay, so the stack is wrong. So it's gonna be like fork. The closure, right. So the closure of the fork is going to be null. Okay. And this is just the R register. Okay. I see. I think what we'll do actually, instead of saying R register, we'll say init absolute keep 0. Okay. Because, okay, the reason why it was R register before was like because I just had to put something there. And in my mind at the time, I thought that this would never be used in any circumstance as something that would be evaluated. So it didn't matter what it was, what the value was. I just had to have some kind of easy way of just saying, hey, I want this to be whatever. This is like undefined. It's basically like undefined. But I'm calling it null because it's funny. And but now it's like, okay, well now it technically is kind of accessed in like a meta way in the zig system. So, okay, well let's just say that it's like a more acceptable value to be used in that situation, because this would be turned into, actually, wait, no, it actually has to be turned into an, wait, no, this doesn't work. It actually has to be a valid heap address that points to something else. That is the issue here. I think maybe we'll add a special case for if we get a heap value that points to 0. Okay, let's do this. Let's add is null. Oops. Yeah, because this will just turn. This will just be heap. Yeah. So it's like, okay, if we're heap and the absolute address is 0, that means it's like a null thing. So there we go. Hello, Blue. What's up? Is it also super late for you? I'm probably gonna quit here in a moment. I just really want this to work here. It just feels like we're so close to get this working, and it's such a huge hurdle here to get past, and we're so close to getting it. Okay, so these are null. So now we go to the evaluator and resolve location, and it's like if let's say we have a check at the start to say, well, is this null? then what do we do? Why do we even need to resolve this location is the issue. I think we'll just do from address 0. And it doesn't make sense to dereference this or anything. It's just going to be 0. It's like an invalid... It's like a null pointer, sort of. Not really, but... To address... Oh. Well, it is going to succeed, so I'm just going to catch unreachable here. And I don't think we need parentheses, otherwise the compiler would have complained. Whatever, let's add it anyway. Alright. Okay, so now you shouldn't crash on that. Hey! Oh my god, finally it works. Okay, well, it works in the most basic scenario. So let's go through and see. So this simple program, there's actually a lot of things going on here. And keep in mind, this is like a very unoptimized version of this program. So this is like the most unoptimized version you can have right now. But what is happening is a lot of things. So we set up the streams. Now we're creating the closure for so the instructions of the variable is not really compiled to anything. It's just stored in the read-only data, and then we go directly to line number 2, which is the echo line. So here we create a closure. All of this is creating the closure, and here we're populating the closure with this read-only data, and then we're forking, and in the fork we create a string, which is this string here, which is interpolated. So we're also allocating that there. And here we're continuing with the processing of the closure stuff. Okay, the length of the string is 2, which it is not really, it's not the length of the string. It's kind of like a rope. It's kind of like a string of strings, sort of. Okay, and the number of elements we have is 2 in this, which is because we have one invisible or empty string and then the interpolation. Okay, and then we set the ref to R, yes. So R there is the pointer to the string, and then we set R to be to the dereferenced pointer to the string. So now R is, no, actually, well, first we set this to R, which points to the heap, and then R is set to that as well. Okay, this doesn't actually do much now because R is already this value, but it's there because there's a loop, and in every iteration this is done so that R is like reused every loop. Okay, and then R plus 1, so the first element of the string rope kind of thing is set to an empty string. And then we go to then we reset R to point to the string again, and now we set the second element to be C plus 0, it says here. So that is like the closure pointer. Now, for the first time we see in the debugger, the closure pointer plus 0. So we're dereferencing the first, so we're getting the first element of the closure, basically, which is just this hello world thing here. And if we look at the heap now, we look at the stack, 3 points to the closure of this thread. So we can actually look at the heap at that instruction. And we can see here that the closure here starts here. And the one element that we have is this read-only data element. So if we type data, no, okay, I don't think, maybe we can't see the read-only data, but basically it's the hello world, it's this string here. Okay, and then here's the start, here's the heap here, here's the start of the string rope thing. Here's the first element, which is a 0 length string, and then the other element is going to be set right now. So if we say step, and then we do this again, we can now see that the whole string is now populated with these correct elements. Okay, so this is now pointing directly to the read-only data, and then we step again to pop the string pointer of the stack, put it in R, we push it back, kind of unnecessary there, but it's as this is like highly unoptimized, and everything is done for safety of compilation, so that is correct. Okay, and then we push something, yeah, that's the echo, echo, literally echo, and then we push 1 for, so now we have the arguments. You can see here 4 is pointing to 12, which is the string rope thing that we have as an argument, and then this is the first argument, second argument, you could say, in the argv, and then this is the number of arguments after the first one. So that's why it says 1 and not 2, and then we execute that, and that gets executed, and now echo is spawned with that argument, and then we simply wait for that to stream out, and there we go. Now we get the hello world. It takes a couple of cycles for that to push through. I'm not sure why it takes so long, but it does. So, and then the thread is done, and the main thread is also done waiting, and then it just exits 0, and then we get some error for some reason. Index out of bounds. Okay, I think this is a debugger thing. Yeah, there's a debugger issue there, but yeah. So this finally this works, and this probably, like, we should test this as well. Like, if we put this in a block, it should also work. Yes. Oh my god. Okay. Because this is also run in a separate thread. Like, now we have 2 layers of threads happening. So we actually, S needs to be populated in this closure and this closure. So we actually have 2 closures being created now. So here's the block thing happening, and a bunch of pipe options being set here, and here's the closure for the block. And here's the fork. All right, and then you fork immediately. Again, right, that's the block stream fork. Okay, And then we created another closure there. Okay, so basically it works. But now I want to try some more advanced stuff. So actually, if we go to bindings, the original thing here, all this should be set up to work here. Actually, you know what? Let's do this again. Because I didn't try. So this example obviously is the most simple example we can have. That will work for basic, very basic closures here. The problem is that, or the thing that I want to test is like this S now is a read-only variable, okay? But I want to test it's stored in the read-only data. So what I want to test now is to store it on the heap and see if that still works. So to be able to make it stored on the heap is basically we just need to add one interpolation to it, and it will be stored on the heap instead. So if we just do this, even though technically this could be stored in the read-only data, we don't have that optimization right now. So this actually is translated into being stored on the heap as a kind of like a rope string thing. So let's see if this works. And it does. Wow. Okay, so that means that the closures do work for both read-only data. It also works for heap stored things, and yeah, very cool. The thing that is kind of magical here is like the string materializing part, because when we turn this into a string, or yeah, when we kind of I'm saying turning into a string, it looks like a string, although it's not technically a string. It's actually like a slice of values where you're kind of you have like literal strings spaced out by or interspersed by expressions, and these expressions could be pointing to, you know, this points to the read-only data, but it could point to the heap, it could point to, it could be anything really that is a string, or it could be turned into a string. It could be a number as well. So that is kind of what's kind of magical here, is like everything that you put in here, but it fits, you know, the kind of scripting language style where, you know, everything is able to be coerced into strings. So it's like if I put a, let's say I put a number here, so I put 0, okay, that should still work because it's coerced into a string when we evaluate it. So you don't have to kind of like, you don't have to like in Python you would do something like this, or but it was still, we can do this. We can leave it up to the programmer to determine how to turn it into a string with using other functions probably. But now this is how it works here. But yeah, awesome. So that's what I wanted to test before we try to do this whole file here. I'm just gonna press F5 here and it will be an error. I'm not sure if it's related to, like, let's say I add another echo here. Yeah, so for some reason when we have multiple execution calls, there is something going on. So I'm gonna go over here and just, because one is fine, right? But then when we just add one more, we get it and save, we get an error. Okay, let me just look at this real quick and then I'll call it here. Index out of bounds, context, private stack, stack frame plus apply, okay. Run instruction 425, okay. Destination. Okay, let me take a look here. So evaluator 425. Oops. Wait, did that actually be it? No, that's the end. I was like, I don't have 4,000 lines of code in this. I barely have 1,000, so yeah. Okay, so this is the set instruction. Okay. And we're trying to get the destination, so let's see where this goes wrong. We could go through the normal debugging process here. I'm not sure where the error is happening. I didn't look too close here. So here's the first one, and that's fine. Where are we now actually? Okay, so that waited. So the first one actually, yeah, we do get echo hello world out here. Good. And then, and here's the second one. So we create the closures. Okay, there we go. It's when we try to set this ref +6 to R. So is this the issue? It says +6 here. And we can see on the stack there's no +6. It's goes up to 5. Why does it say 6? So let's go to the compiler, and it's gonna be like compile executable call, I think. So so we start at 4. Every thread starts at 4, and then we add 2 for each closure, I believe. So this increases the stack size by 2. So it would make sense that we would have, oh well, 0 is included, so 0, 1, 2, 3 is the first 4, and then 4 and 5 would be the first closure. So 6 and 7 wasn't actually... Let's see this again. So we have 2 refs there. Very good. And we do stuff with those. Actually, you know what? Those are popped. They're popped over here. Oh, I know what's going on. Okay, I know what's going on. So it's like we have an internal counter for calculating in compile time which stack address relative to the stack frame we are referring to. And let's say we have like the pop instruction. The pop, not this one. Well, here you can see that this is like how we add the pop instructions, but we're kind of circumventing some logic that we have in other places. So that is the issue. Here we go. Here's a pop. So what this does is we're not only adding the instruction, we also do this. So that's the issue. We need to do this as well. Which it could be an issue, actually. Or could it? No, it's probably not an issue. Because the problem is we're kind of doing that after the fact. Like, this is happening after the fact. It's like we're inserting a bunch of instructions after we've compiled some previous stuff. So it's like if that relied on, if things like after the fork relied on the stack relative counter, that is an issue. But I don't think we ever do that. It's gonna be an error in that case. It's like whenever we fork, we basically want to set up a closure. And whenever we set up a closure, we kind of want to handle that directly after. Yeah. So let's see. Whenever, so how would that work? So basically we're looking at this. We set this back to original instruction set. So we are working within that. So basically we can do this. I mean, we can do this just to make it super clear that this is part of the pop instruction. So we have to do that. We don't have any push or anything. We only have like alloc. We have set, fork, set, pop, pop. These two need to modify this counter here. Because otherwise we don't know. Like, I'm not sure how other compilers do it, but basically this is how I did it. It's like, I know that we have a current frame. That is like runtime known. The frame, the stack frame basically. And then we have like a relative stack counter so that we can refer to each identifier. They get like, you know, an address, but the address is relative to the stack frame. And that's how we can know what we're talking about. So that's how we can refer to that. So that's it's very important to have this in sync, because otherwise you're referring to the wrong thing. Okay, I think that's, yeah, okay. There we go. Cool. Great. So now let's go back here. Okay, that was an easy fix. And this also works. Okay, awesome. No, let's go over here. Oh, still an issue. Unsupported wait T. Huh. $20? Strange. Unsupported waity? Waity? Okay. Interesting. I wonder what is actually causing that. Is S even referenced anywhere? No. I think if we do this, that should work as well, but that doesn't really change anything. Okay, you know what? I'm gonna remove things here. I'm just gonna remove these blueprints and stuff. Alright. So, the error is happening over here. Let's see. I want to have like a more simple example of this actually happening. So let me remove this. Still happening, yeah. And let's also remove the Y here. I'm just gonna do like echo X in here. Okay, that works. So is it because we have a Y? Okay, that works. But okay, so Is this the issue? So this is now like a heap stored thing. And of course we're creating... so it is a big difference between this and this right now, because this is stored on the read-only, so we don't even need any instructions for this to exist. But this, on the other hand, is actually gonna be a bunch of instructions now being spawned here. So that is the difference. And then of course it's used down here. Let's see if this also is an issue. Yeah, so this still is an issue. So basically it's more of a block issue. Oh, this doesn't work either right now. Okay, well, let's do like blocks bindings, combining the two. Alright, let's try this. So that should be the same issue there, yeah. So now we have the most basic example, I think, of this issue. And I know I said that the previous thing was the last thing I was gonna do, but I think I was lying. Let's just take one look at this. Fork. Creating the block things. Creating a closure. I don't think the closure matters here because we're not really using it. Alloc 0 is kind of weird. Yeah, that is actually strange. Is that the issue actually, Alloc 0? I don't know, maybe not. And fork. So here's that fork, that's the stream fork. And pushing R to save the stream fork thread handle. And we're creating the string there. Size is 2. Alright, so first element is a 7 length string from the read-only data. That should be hello, comma, space. Very good. Next thing is world, exclamation mark. Okay, that's all seems fine. Pop. So we pop 5. So we pop, yeah, we pop the string. We always pop the string, yeah. And then we create a ref, identify ref. Okay. Interesting. Wait, identify ref. And we set that to R. R is now pointing to the string. So now the identify ref is also pointing to the string. The pipe is turned off because the block is done. And then we pop. Okay, so the identify ref is never popped, is what I'm gathering here. Okay. So it's like, okay, it's like if we're trying to get a closure thing, we declare the value. Why are we creating a ref? An identify ref that never gets popped? That is the question. I don't even remember that. So that is happening in the binding. Right. Yeah, okay, yeah. Because we're looking at, okay, well, if the result is using R, we actually need to save that because we want to use R as well. So we create a ref to store R in there, and then the result is going to be the dereference of that ref. But the problem there is that we never pop it later. That's the problem. So we can't really do that. It's kind of like, yeah, we're using the stack, but then we're never popping it. How do we solve this here? I have to kind of context switch a little bit here to understand how to fix this here, because I did this, I don't know, last week or something. That was a couple of streams ago. So the problem we're trying to solve is that we can't just return R. Wait, so if we have a result, if this wasn't the case, the result would be something else, like a read-only data pointer or something. And that's fine to return. But if it's an R register, that means it's something that has been, that is kind of like volatile, and we have to kind of save it somewhere to make it a stable thing. But the problem with making it a stable thing on the heap, or I mean on the stack, is that we actually don't consume it later to pop it off. That's the issue. Also, this happens when we bind it, so it only happens once, and then it has to be popped at the end. I think what the logic was that it didn't matter if we popped it or not, because we would pop it in the end anyway when we restore the stack frame. That actually like pops everything. However, now we have an issue because this binding is like messing with the stack in a way where it doesn't work anymore. So I have to kind of go through this again, because right, so there, no, alloc 3, yeah, so now stack 5, I'm not sure what that is right now. Oh, that's the string, right, that's the string, yeah. So we're building up the string here. Yeah, we're building up the string. We're popping that off. So now it's like well, this points to the string. R points to the string, right? And it's like, okay, well, we're trying to bind Y to this result, and we see that, okay, it's an R result, so we have to save it now somewhere. So we create it, we push on the stack, we push this thing on the stack, and we store that there. So now we have that stored here on 5. which looks weird because it's the same pointer as the heap, but I guess that's fine. I guess that they share the same address there. Okay. But now it's like when we pop here, we kind of assume that we're working with a thread, which is not the case, because that was pushed over here. So actually this is like this compilation unit. I'm not sure if that's a correct terminology here, but basically when we're doing the identifier binding thing here, it doesn't restore the stack balance. So either we always restore the balance, or we cannot assume that but that is kind of, we have to be able to assume that we can pop what we push. I think we should always restore the balance, unless we have a mechanism where we kind of take this identifier and then we consume it somehow, like at the end of the scope. So that would pop that at the end of the scope, which would be here or before this. So we're saying, okay, now we're at the end of the scope, and then we pop the thread and then we wait for it, or something like that. We could also maybe say that we could also say that the thread has like a reference instead of, yeah. I think that makes more sense actually, instead of popping it, because popping doesn't really matter. Yeah, okay. Yeah, because then we don't actually need to restore the balance. Yeah. So that would be compile. Where is that? No. Where was that block? So let's see, closure. Where's the fork? So here's the fork. We're pushing that. So here we're kind of storing it on the stack. However, instead of pushing, we want to do new ref block thread. Okay. And then we'll do set location is well, this is the standard output. Ref, so that's the ref. So this is standard. Right. So we have the ref. We set that to this. All right. And then we don't push. So instead of pushing, it's kind of the same thing here, except we're naming it and we also have like the address to it. So that's the difference here. So this also pushes to the stack, but we have a name and we have like a point, kind of like a pointer to it. So, and then we set, but now it's two instructions instead. But I really want to change this so that ref is actually like one instruction, or that we build it into push to actually get the reference to it out instead of having to do this. But yeah, whatever. Anyway, so now we still have it on the stack, but now we can actually reference this instead of relying on the pop later, which we don't really even need to do, because when we pop the scope, well, no, Where is that happening actually? There is some kind of frame popping somewhere. Don't we have this here? Not sure actually. Maybe it doesn't matter because it's like at the end of the thread anyway. So it doesn't actually matter. Yeah, it turns out that like the stack is like, since all function calls are happening in their own like virtual threads, we don't actually need to restore the stack. Like the stack, we can just yeah. Anyway, so okay, so we set that to that, yes, and then instead of popping over here, we're just gonna use the ref instead. Okay. And you are a location, so I'm just gonna do a dot from there. Okay. So does that fix it? No? Still unsupported YT. Do we have a... Okay. Let's see what's happening here. Where's the fork? Here's the fork. Right, so see here. Now we're creating a ref. That should I'm pointing with my finger here. That should create another thing on the stack. When we get back to here, there we see 4. And then we set that to R, which is now the thread handle. So that should be correct. This one, yeah, thread 5. That should be correct. And then we're creating the thing. Pop in the string, yes, identify ref. Okay, now we're saying wait for this, which should be thread 5. Okay, we might have to dereference as well. Yeah, so that might be the issue. So we just need to deref this. There we go. And let's just echo this so we can see that it actually works as well. Okay, there we go. Oh, finally. And then let's go back to the bindings example now. This now does not error. And let's go back to well, let's just do that. Hey, there we go. Okay. Wow. Okay, that works. All right, that is huge, because I spent so much time trying to figure out how to do this. I mean, it turned out the problem is I wanted to do it in a more simple way. But it turns out we had to I wanted to kind of try to be able to wire it up directly somehow. I'm not sure exactly what I was thinking, but it turns out that what I did now works. But I mean, what we're doing is basically we're keeping track of okay, X is referenced. It's the X, this means this X, but it's referenced deep here in this nested structure over here. So what we're doing is we're because we're kind of passing thread boundaries here, we're creating a closure for each thread. So this is one thread. We're creating a closure where we define X and Y as well to point to places in the closure, in this thing's closure. And then this also has a closure, this block here. And that's just, they need a closure because they are running in separate threads. That's basically why they have their own closures. But it's also nice to have the closures because of, you know, the functions that we're gonna, like functions calls, of course, are gonna need. But it turns out these simple things also needed closures. I mean, there might be another very simple solution that I don't see, but I've spent a bunch of time thinking about this, and this was the solution that I came up with, and which also played into future requirements as well. So, and it wasn't too bad. I mean, sure, it was. There's a lot of things going on with the closure and stuff, and it's not super simple, but it was kind of. Well, it was way more painless than I thought it was gonna be. We basically just have these scopes that we build up during compilation in a stack, and then whenever we encounter an identifier, we say that, okay, well, is this declared in our current scope? Then we just use that value. If it's not declared, okay, then we try to grab it from the outer scope. We go one depth above to see, okay, well, is X declared in this scope? No. Okay. Then we grab it from the next scope above. So, and then along the way, we also create closures for each one that hasn't gotten like a closure yet. So basically, once X and Y is added, they are added to the closure list, and so the closure gets, and then we know what we need to populate the closure with and what are their positions in the closure as well. So we get like a stable address to the things and where they are like relative to the closure, and yeah, it works. The only thing that I need to kind of think about now is the mutability thing. Like this works well for constants. What about mutables? That would be the next issue to tackle with this structure here. Also, I'm not sure if I want to tackle like functions right away after this, because that also is like, yeah, I want to at least think a little bit about how this works into functions, because it definitely doesn't feel straightforward. It feels like we just have to figure out some rules for the functions and try to work our way forward there. But yeah, very nice here, progress. Very, very, very cool. And yeah, that's gonna be it for this time. So thank you very much for joining me here, and I'll see you later.